Okay, guys, so let us start our today's seminar. So this time it's in English, and I think it's good practice for us because most of our seminars are in Russian. So sometimes we need to have a seminar in English as well. And our today's speaker is Diego Gransol. Gransol or Granzol? How it's pronounced?
Good. Very good.
Gransol. Yeah. So he's a friend of our group. He visited us a couple of times in past. And actually, he was a person due to whom I've got interested in exploring the properties of loss landscapes and deep learning. And I'm very grateful to him because we've got some interesting results after you left us last time. So Diego already gave us presentation once. So today is his second try, and today's talk will be about the application of random matrix theory to optimization and generalization in deep learning, right?
Yep. Thank you very much. Sorry, you want me to? Okay. Thank you very much, Dmitry, for the nice presentation. Yes, as he said, I was very lucky to be able to visit his group and learn from the great scientists in Moscow and spend some time learning things in the city. And so it's a pleasure to be back and present some slightly more recent results. So as already said, my name's Diego Granzol. I originally had a physics background from Oxford. I then did a PhD at the Machine Learning Research Group, also in Oxford. And I started off looking at information theory and maximum entropy. And then I moved into deep learning theory with applications in optimization and generalization, some of which I'm going to be showing today. So I'm going to start off basically by talking about one of the largest contributions during my PhD and extended in my time as an AI theorist in Huawei, which is a random matrix theory approach to mini batching. And this basically answers quantitatively the question, how should I change my learning rate as a function of batch size? And this has some quite interesting results, some already known for SGD in the context of other frameworks, and then some not known, such as adaptive methods, such as ADAM, that we're going to touch on today. And then I'm going to talk a little bit about actually the theory behind a method actually developed in conjunction with Dmitry's lab, stochastic weight averaging, a little bit more of a rigorous understanding as to why it necessitated the particular regularization and large learning rates and applications to also adaptive methods to get very good test error results on benchmark data sets such as ImageNet and benchmark networks such as the ResNet. And then just at the very end, I'm just going to talk a little bit about a practical side project that I've been investigating on the side, which may be of interest to some people in the group for some potential collaboration. So just a little introduction on the notation. For an input-output pair x, y, and a given prediction function h parameterized by a weight vector w and a loss function L, we can just define the true risk as the expectation of the loss under the data generating distribution, the empirical risk as the loss over the entire data set, and the batch risk as the loss on a mini batch of data B, which is subsampled from the data set of size n. And so my essential initial insight or idea, you could say here, is that we know for the convex quadratic case that the largest permissible and optimal learning rates are given as functions of the eigenvalue of the Hessian. So some of you that are familiar with the work of Polyak and Nesterov in the optimization community, which is very strong in Russia, may be familiar with some of these optimization rules. Typically, they're framed in terms of the Lipschitz constant L and the strong convexity constant mu. And the Lipschitz constant L is just the largest eigenvalue over the entire space. And the strong convexity constant mu would just be the smallest eigenvalue in the case that it's positive definite over the entire space. So this is just locally the same thing. And so my thought is if I can understand how the batch Hessian varies from the empirical Hessian, then I should be able to understand how my learning rates should change as a function of batch size. So the simplest approach that I had here is kind of as shown in equation 4, what will be known as an additive noise model. So I just assumed that the batch Hessian is just given by the empirical Hessian plus some additive perturbation. Now, simple algebra basically gets you these relations, which basically says that we have in expectation the elements of this perturbation or fluctuation matrix is 0, and the mean square is given by this factor 1 over b minus 1 over n times this variance element wise of the loss function. Now, that in of itself is not actually enough to give me a kind of nice analytical relation, which is what I wanted to derive. So the second insight here is that if I can either assume or show that this fluctuations matrix can be modeled as a random matrix, the simplest of which you guys may be familiar with is known as the Gaussian orthogonal ensemble, which is just element-wise IID normal and gives the Wigner semicircle limiting spectral density. Then I can basically use results in the mathematics literature for perturbations of large random matrices to understand how the spectrum of the batch Hessian is related to that of the empirical Hessian. So I could either just assume it outright, or I could, just using certain kind of other assumptions more common in the optimization literature, such as Lipschitz continuous empirical gradient, derive these relations. So the other thing that's worth noting, as I said earlier, is that things become much easier if I assume that these elements are all independent. Now, that's a little bit of a strong assumption, very likely not met in practice. So the weakest assumptions that we can go by is basically that we can add some dependence between the elements, basically in the form of this sigma algebra, but they need to basically satisfy certain conditions. And so these technical conditions are given here in 1, 2, and 3, and just put in simple words, the condition 1, or I, basically means that you're allowed to have dependence between the elements of this fluctuation matrix, but the dependence cannot be too large. So you cannot have too many dependent rows and columns. Similarly, so the variance element wise, it doesn't need to be IID. You can have different variances in each of these elements of the fluctuation matrix, but overall the variances cannot differ too much. And thirdly, these variances must be bounded. Now, of course, the bounded variance assumption follows strictly from this Lipschitz continuous gradient assumption, which is common in the optimization literature, but this is the minimum you need. And now under these assumptions, the limiting spectral density of the fluctuation matrix converges to Wigner's semicircle law. And now, under the further assumption that the empirical Hessian is low rank, which we're just going to get to in a second, then we get a very nice analytical relation here of the largest eigenvalue and the spectral norm. And some of you might be familiar how this spectral norm is going to come in for the learning rate in a second. But the largest eigenvalue of the batch Hessian, as long as the eigenvalue of the empirical Hessian is basically outside the width of the semicircle, is given by the largest eigenvalue of the empirical Hessian plus this perturbative factor, which is basically in the small batch limit proportional to P over B and this variance of the Hessian term. And otherwise, it's just swallowed within the noise matrix. And so it's just worth saying that this assumption on the low rank nature of the empirical Hessian can be relaxed. We simply need non-interacting eigenspaces. This is known as free addition in the random matrix literature. But it's worth saying that empirically, the full Hessian of true neural networks does actually look low rank. And by does actually look low rank, I mean, is because we have Hessians which are basically millions by millions, or even can get up to billions and billions size matrices. We cannot even store the matrix, which is a p squared operation, let alone eigendecomposed, which is a p cubed operation. So we need some way of estimating the low rankness of this matrix. And this is done here using basically Hessian vector products, which allow us to generate a moment-matched spectral approximation to the Hessian. And so we can basically just estimate the spectral mass near 0. And this is shown here for the generalized Gauss-Newton, which is an often used positive definite surrogate of the Hessian in deep learning second-order optimizers. And for the Hessian, we see here a very, very high proportion of estimated 0 eigenvalues, over 99%. So this looks actually well met in practice. I'm not going to go too much into the details, but those of you with...
Wait a minute. What is shown on the x-axis?
Sorry. Yeah, so this is just basically throughout the trajectory of the optimization. So this is epoch 0, epoch 50, epoch 100, epoch 150, 200.
Okay, and on the y-axis? It's what
This
is
here-
the direct of zero eigenvalues.
Yeah, this is the proportion of estimated zero eigenvalues. And so because because we don't actually eigen decompose, we basically have like an estimate of the mass at that point. And so this here is showing the estimate of the mass, and this is showing the actual value of the mass. And you can see here it's very, 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 very close to zero.
Ah, okay. And what's the difference between A and C? So GGN and Hessian?
Yeah. So GGN is just a generalized Gauss-Newton. It's another matrix that's often used specifically to approximate the Hessian, or it's used in optimization often because it's positive definite or positive semi-definite. And so this is the Hessian. So you can just consider C and D, but often I just looked at both matrices because both are of interest and both work well under this random matrix theory framework.
Okay, and what is shown on the y-axis on B and D?
This is just the value of basically the point which I'm taking to be near zero. So when you do this kind of moment match spectral method, you basically get a point on basically the eigenvalue space and the estimated spectral mass at that point.
Yeah.
It's a discrete spectral density approximation, right? So you could then smooth it and do some integration, or in the case that I did here is I basically took the value closest to zero and I just looked at its spectral mass. And I'm just saying it's consistent with the hypothesis that there is, that both these matrices are very low rank. Because of course, if it was very, very far away from zero with a very big spectral mass, then it would not be consistent with this hypothesis.
Sure. Yeah.
So probably if I was a more rigorous statistician, I would try and do some statistical test.
Okay.
So following on from that, it's actually worth saying that for the case of a feed-forward network using ReLU activations, you can actually derive a rank bound. And I won't go through, it's just algebra to get there. But the basic idea, which is quite interesting, is that the rank bound basically depends on the number of classes times the number of neurons in your network. Whereas the number of weights is kind of the sum of the product of adjacent layer neuron numbers. So for real neural networks that become quite wide and quite deep, this basically can give actually a pretty nice rank bound. And I showed here for CIFAR 10, we here get this 96%, even though we're actually seeing 99%. But we're saying that it doesn't just need to be based on an experimental analysis. You can also derive a rank bound. So any more questions on that experimental stuff, or can I move on to seeing the effect in practice?
I have a question about augmentation of data. Can we say that if we augment data, then we lose this low rank assumption? That your low rank assumption is actually an artifact of using a finite training set.
No, actually, no, it's not. So typical low rank assumptions do often depend on the number of data points, but not here. And actually, I can show you these results perhaps offline, but I have actually run the Hessian using like the fully augmented data set. So by which I mean for CIFAR 100, instead of 50,000, we were using 5 million. It took absolutely ages to run. This was actually done back in my internship in the Bayes group. And the spectrum actually looks very similar. So I'm happy to discuss that offline, and I can actually share the code with you and you can run that experiment yourself. But that doesn't actually make a difference. Not a significant one anyway. It's not like the sample covariance literature where the covariance is basically bounded by the number of samples and often taken to be small.
So what is the source of a low rank here? If it is not the size of a training set, what, the number of parameters of neural network, or what? Why the Hessian is low rank?
You just have to go through this algebra. We can do this together offline if you want. It's basically just the structure. It's just if you follow through the algebra, you get this result. There's not really much more to say than that. basically the rank depends on the it depends on the paths that you can take. And this will depend on the number of neurons, not necessarily the product.
Well, we know that, for example, in logistic regression, we would not have any problems with a low rank. There are no low rank Hessian there. Yes?
I'm not sure about that, no. So experimentally, even for logistic regression on something like MNIST, when you have the full data set, and logistic regression, you can actually fully eigen decompose, the Hessian is very low rank. It may not be 99% low rank, but it may be 95%.
Okay.
So that's worth it. If you have theoretical results that go against that, we should definitely pick that up online, because my experimental results for logistic regression are also low rank.
Okay, let's move on.
Okay, cool. But thank you.
One more question, please. I'm sorry.
Sure.
So I wanted to ask about the assumptions you have here actually to derive this low rank Hessian. We discussed that the main thing is about the rows of the Hessian. I mean, what you said about
no. So this low rank assumption is simply just algebraic, running through a feed forward network with ReLU activations and softmax output and cross entropy loss. That's all that's required. And that's just an algebraic thing that has actually nothing to do with the random matrix theory assumptions here.
Okay.
Those are two different things. So it was simply, I needed this low rank assumption to get this nice analytical form. And I basically wanted to justify this extra assumption here. And one way to do that is just to empirically look at this. And I noticed that, you know, it seemed to be getting more low rank as I went from logistic regression to MLP to deep neural networks. And so I decided to derive a rank bound, you know, but something that these reviewers, so this actually should be getting published in JMLR, should be even this week. The JMLR reviewers quite like this bound, but some other reviewers, you know, pointed out the dependence here on the number of classes. But now also note that if the number of classes increases, then usually the number of neurons in the hidden layer also increases, but it is less good as your number of classes gets bigger and bigger and bigger. So I'm not crazy, you know, pumped about this low rank bound. I don't think it's amazing work, but I think it's interesting nonetheless to say that it's not just needed in the random matrix theory context, but it's empirically verified and it has some theory behind it.
Okay, I see. Thank you.
Okay, yeah, let's move on and we can talk. There are going to be more assumptions, so more to talk about anyway. So we can get to that near the end. So here's just showing the effect in practice. This here is for the VGG16 on the CIFAR 100 data set, and you're just going to have to trust me that it looks similar on a bunch of other networks and data sets. And here we just show the spectral density, and here we show the eigenvalues. And here you can see for the full data set, we have a largest eigenvalue of 11.41. And here for a batch size of 128, we have a largest of 80.15. And we see the same kind of broadening here of the outliers. Now it's worth saying that this batch of 128, this is a stochastic estimate. So for each different batch, we would expect slightly different results. Now, this basically is actually covered in our theory by looking at what we essentially call this Kolmogorov limit, which is that P, B, and N, so the network size, the batch size, and the dataset size all go to infinity, but their ratios have some constant value, which is greater than 0. And all this assumption basically means is that our entire result is characterized by our mean. So what we have here theoretically is basically what we would expect in the mean value case. And so we will have some variance around that. So the interesting thing to note is that even though each batch of 128 is going to be different, in expectation, it will be broadened by the amount given by our formulas. And this is actually what we're going to test in a second. So the question is, how do we test this? So what we need is we need to be able to estimate this quantity here, which is basically the element-wise variance in this fluctuation matrix epsilon. And so we actually calculate this by looking at the variance of the entire Hessian, which by our model just depends on this fluctuations matrix because the empirical Hessian is a fixed object. And so using this, we can actually check our agreement with theory. And so the model I've shown you before, which is this additive noise model, is basically given here. And what we have here is basically going throughout the optimization trajectory in a gridded fashion of 25 epochs at a time. We have the full data set eigenvalue. In orange, we have our prediction using random matrix theory. And then we run, for a batch size of 128, we run 10 different seeds, and we plot in blue the mean and plus minus one standard deviation in a shaded blue. So you can see here we're kind of within one standard deviation. Here on the right, I have another model, which is a little bit more sophisticated for the generalized Gauss-Newton, which is basically an additive plus multiplicative noise model, which you can see has a somewhat better fit. I didn't present this today because I thought it might just be a little bit overly involved for people that are not familiar with either random matrix theory or deep learning, but it's all available in the paper. Now, there is actually some good papers by someone in Stanford called Vardhan Papian, who looks at basically arguing that the largest eigenvalue, so which is what we're looking at here, we're looking at the largest eigenvalue, lambda 1, is actually given by this generalized Gauss-Newton for the Hessian. So it's unsurprising that this model actually works a little bit better. So that's that. And so there is one thing to mention here, which was actually brought up by the JMLR reviewers. They basically said, well, in your theory here, we kind of see two regimes. We see one where you have these kind of outliers and they're broadened, and one where these outliers are swallowed up. And so we kind of like to see these two regimes. And from my work looking at spectra, I was always familiar with seeing these outliers. So I kind of had a hunch that we were always going to have outliers. And so this is just a little bit of an investigation on exactly that phenomenon. So this is just a single layer, multi-layer perceptron with a Gaussian mixture model data. And we see here at initialization what the spectrum looks like. And we see here at the end of training how the outliers have actually kind of broadened in size and gone further away from the bulk and from each other. And it's actually very interesting that, again, this Vardhan Papian paper, he basically proves this result for logistic regression. This is something I'm actually collaborating with a colleague at Huawei right now, is to basically extend that theoretical framework away from just logistic regression, but also the one layer, multi-layer perceptron. And so in terms of constructing a spectrum where there are no outliers, so the closest I got here was using this VGG16, which you see here at initialization also has an outlier, admittedly quite a small one, but it's separated from the bulk. But if I train it using a very, very large learning rate, no weight decay, to a point of no return, by which I mean I train it with such an extreme learning rate that the network is basically very close to having diverged. It hasn't diverged, but it's close to having diverged. And no reduction in learning rate brings it back into a regime where it learns. Then you're able to basically bunch this up here. And you could argue this is no outlier, but then you can't actually train it. So in all cases where training actually happens, you have outliers. And this is relevant here because this is going to come into basically how we look at learning rates as a function of batch size. So just to kind of capture in a small infographic the result using both the Wigner noise model and the Marchenko-Pastur noise model for the generalized Gauss-Newton. If you start off with a small batch size and you increase the batch size, you will initially get near linear gains, as shown, because this term here, the second term, dominates the first one. So as I double the batch size, I'm very close to halve this size. And then beyond a certain point, as you increase the batch size further, you can no longer get any appreciable decrease in your spectral norm. So this basically, as you can already imagine, will say that beyond a certain point, if you increase the batch size, you don't reduce the spectral norm and you can't increase the learning rate. So how do we tie this in to the learning rate? So we want to look at basically what is the largest learning rate that we can use so that in expectation, we don't actually increase our loss. And this is basically given by 2 over the inverse, 2 over the largest eigenvalue of the batch Hessian. Now this is a bound, but if the gradient is actually aligned with the outlier directions, which other work by Gurian now has shown is the case, we basically get very much the same result. So how does this actually hold in practice? So here we see here for the no batch normalization, no weight decay case on the VGG16. So I very much like this VGG16 architecture because you can train it to reasonably good results without certain tricks like batch normalization, and you can add batch normalization. So you can really do nice ablation studies. So we see here that the curves, as we double and half the batch size, is actually almost exactly follow the same trajectory up to a threshold when we increase the batch size too much, and it starts to get worse and worse and then no longer train at all. And this happens also in the same way if we use a different learning rate schedule. So here I've actually used twice the largest allowable learning rate schedule, which initially decreases very nicely, but then diverges, and they all follow the same path up to a point where they then no longer train. And we see the same result here also if we use batch normalization and weight decay. So one difference here, of course, is that if we just use vanilla batch normalization beyond a certain small batch size, you can no longer compute, the variance of an object if you only have one sample. And if you have 2 or 4, the variance estimate is very, very poor. So in this case here, not shown on the graph because it would make it too messy, you can actually reduce this down to a batch size of 1, and it continues down the curve very nicely, whereas this is not the case for batch normalization, but this is to be expected. And we're saying that also this holds for other networks, such as here, the wide ResNet on CIFAR 100 with batch normalization, weight decay, and also for ImageNet.
Diego, wait a minute. You're talking too fast. Please return to the previous slide.
Sure.
I didn't quite understand why it happens that the increase of mini batch size leads to divergence of the network.
So sorry, say that again. I didn't understand the question.
So here on the left plot, we see that if you increase the mini batch size, then the network starts diverging.
Maybe I didn't make it clear. To basically show this relationship that the learning rate, basically, I want to show that this relationship is meaningful in practice. Yeah, here in equation 7. And the way I do that is by relating this largest eigenvalue of the batch Hessian to the largest eigenvalue I can use so that the loss doesn't increase in expectation, right? And so I do that by basically increasing the learning rate proportional to the batch size. So this is given here by alpha naught.
So the different plots here correspond to different learning rates or to different mini batch sizes?
You mean the different curves on the plot?
Yep.
Yeah, they're basically, you're keeping this relation, but then each line will be a different learning rate and different batch size. So for a batch size, go on, sir.
You're increasing the mini batch size and you're increasing the learning rate in the same.
Exactly. And I'm just saying here that the proportional increase and decrease, it works up to a threshold. So I'm saying if I just kept decreasing by a factor of 2, it would go down to a batch size of 1 and it would still follow this curve. This is actually in my thesis. I can share it with you. But if you increase it and keep doubling, it comes to a point where it no longer holds and it gets worse and worse till it diverges. And this is what you expect, because at some point you can no longer expect the spectral norm to decrease as you increase the batch size, because this term here, lambda 1, starts to become comparable in size to this perturbation term. I see.
And what can we say about the variance of our stochastic moves? If we increase mini batch size, the variance should decrease. If we increase learning rate, the variance should increase. Yes. If we increase both learning rate and mini batch size, what happens with the variance?
The variance of what exactly? You mean the variance of my estimate or the variance of the curves?
The variance of your stochastic move. So this is a stochastic gradient times learning rate.
Yes. Sorry, do you mind repeating your question?
What happens with the variance when you simultaneously increase mini batch size and increase learning rate in the same proportion?
Variance of the gradient.
Variance, well, not of the gradient, variance of your stochastic move, because you move towards stochastic gradient times learning rate, right?
Yeah. I haven't done analysis on that. I've done everything just in expectation.
Because it seems to me that we have two different factors. One factor tries to decrease variance, another factor tries to increase it. And so it's interesting what will happen if we say increase mini batch size 10 times and increase learning rate in 10 times.
Yes.
So it's
Okay. I see what you're saying. Yes. So what we're doing here, right, is we're using a bound. Yeah. And this bound here depends in expectation on the largest eigenvalue of this batch Hessian. And basically the bound works in the worst case that your gradient is fully aligned in that direction.
Yeah, I see.
And that's the case. And so that's what you're doing. Now you could say, okay, well, how do I know how good that bound is? And you can say, okay, well, that's why I argued here that if most of the gradient is in the outlier directions, we would get that same scaling.
Okay.
And that's basically what I'm testing here.
Yeah. So now I
So I see. Okay, perfect. Cool. So just as argued, we have it here for VGG16, no batch norm with batch norm and weight decay. We see very similar results here for CIFAR 100 and the wide ResNet. So it's worth saying that it's actually a slightly more complicated picture, because here, when you have things like batch normalization, even if you start with a very aggressive learning rate that doesn't work at all, you can still, with the learning rate reduction at the end, recover a reasonable validation accuracy or low validation error, but it will never get to the same level as those that had a stable training early on. So even though you don't get this kind of nice divergence that you have here and then no longer training, we still have, in terms of a kind of actionable learning rate schedule or increase or decrease as we change batch size, a usefulness for the relation. And it holds also for different data sets. And so, how is this kind of practically useful? So, one kind of thing that I was actually trying to achieve in my time at when I was interning in the Bayes group, but I didn't actually quite manage, it came a little bit later, was this idea that, could I at least to some extent in an online greedy way be tuning my learning rate and my momentum based on the curvature. So if I now know that the relevant quantity, if I'm training with the mini batch, is not the Hessian of the full data set, but the batch Hessian, can I use this kind of cheap estimate, which I know in expectation is going to give me what's important, to basically tune the learning rate and the momentum? And so what I've just done here is I've used the kind of relationships from Polyak and Nesterov for the optimal learning rates and momentum as a function of the spectrum. And I've put them against kind of a hand-tuned schedule used for SWA. And so what I simply do is I combine this kind of stochastic gradient descent with Nesterov momentum or with Polyak momentum. And then, of course, to make sure that I ensure that I have convergence at the end of training, I just also use this kind of iterative averaging or stochastic weight averaging. And whilst I don't expect on highly non-convex problems like deep neural networks to in general be better than all kind of choices of learning rate schedules that could be derived, it's at least a positive development to see that we are competitive compared to like a hand-tuned schedule that was tested over many seeds by using this method. And so this wasn't actually tuned extensively. I run this procedure every 20 epochs or so. It's not super expensive because the estimation of the spectrum is done using these Hessian vector products. Each Hessian vector products has the computational cost of 2 gradient evaluations. So if I use a kind of 20 moment matched approximation, I have basically the same as 40 gradient evaluations. So it doesn't even add the cost of an extra epoch of training. So that was quite positive. And so then the next thing, which I think is actually the most interesting result, which I would say is novel, at least I haven't come across this result in a meaningful way, is how this is applied to, different adaptive gradient methods such as ADAM or ADAGRAPH, which others in this group might be familiar with. And so this is something that I presented both in my time at Amazon and in my time at Huawei to different groups. So there seemed to be this kind of idea among practitioners based on this paper here called Don't Decay the Learning Rate, Increase the Batch Size, that we should also be using a linear relationship in the same way we do for SGD, but for ADAM. So if we increase the batch size, we should be if we increase the batch size, we should be increasing the learning rate proportionally. And this is basically based on an equivalent of these graphs A and B. So A is for SGD, where you see that it follows very nicely. We decay the learning rate and we increase the batch size. And in B, they basically argue the same thing, saying that this red curve and this blue curve are equivalent. Now, to me, these curves look very much not equivalent. And the only way they got them back up here at the end is to actually also decrease the learning rate for the increased batch size variance. So for me, I could tell that there was something a little bit wrong here. And intuitively, from this random matrix theory model of the perturbation due to mini batching, it was kind of obvious to me why. And so the basic idea is kind of covered in this algebra. And to kind of bring this forward in an intuitive way, if we look at the relations that we had for SGD, what we're worried about in SGD is that essentially our gradient, our stochastic gradient, is going to be aligned with the largest eigenvector of the batch Hessian. And so we need to basically be careful not to have a learning rate which is too large, that it will in that direction, so that we will basically diverge. Now, for adaptive methods, the situation is a little bit more complicated. And the reason it's a little bit more complicated is that we basically, by changing the learning rate on a per parameter basis, we essentially have a kind of online estimate of the eigenvalue, eigenvector pairs of the local curvature. And so what could happen, essentially, is that we could be more wrong about a direction at the edge of the bulk, which grows here, proportional to root B. We could basically think that this direction is actually a zero direction, when it actually grows as the inverse square root of the batch size, than we are about this largest eigenvalue, eigenvector pair. And so this happens essentially under the conditions set out right here, which we can talk about at the end of the talk, or we can also talk about offline. But it's basically worth saying that if this is done, and this can only happen if the numerical stability constant, or damping as it's called in second order methods, is actually set very, very low, which it often is. It's usually set at 10 to the minus 8. Then we would actually expect the learning rate to increase not proportional to the batch size, but proportional to the square root. Now, this, of course, is only in the case where our batch size is not too small, where, of course, this outlier will begin to dominate anyway. And so just to kind of experimentally validate this, I needed to see that, of course, for Adam, you do have this big, big range in per parameter learning rates, which is here. So here I just opened up the optimizer during training to actually have a look at the, this is just the density plot of these per parameter learning rates, which you can see do have huge variation. And I also needed to be convinced that it does to some extent learn this largest eigenvalue, eigenvector pair quite well. And so the way I did this was basically by running Adam with a numerical stability constant of 1. So to basically limit the ability for this kind of wrong estimation of these very, very small eigenvalue, eigenvector pairs, and see what the largest learning rate that I can run this by without divergence. As you can see, it's actually much, much larger than that of SGD. So it is to some extent convincing that it does learn this largest eigenvalue, eigenvector pair. And so here is the training curve result, which you can see is quite convincing. I find the largest learning rate at the batch size of 128, which is the typical batch size that we used in these experiments, that trains. And then I basically scale it with the square root up and down. And you can see actually very nice experimental agreement, again, up to a threshold. And, you know, it's worth saying that this is you need to really test the theory at the point at which it's going to break down. Otherwise, it's not really allowing you to falsify your hypothesis. So in the case, since we know that we can always train neural networks with smaller learning rates, this often doesn't lead to particularly good generalization. We want to see in the regime where we're being very aggressive, which for a square root scaling rule is as we go down. And so you can see here for SGD, if you try the same procedure, you try and train on the way down, which is more aggressive, using a square root learning rule, you see that you get actually very bad performance followed by divergence. So it is really a very different regime for these adaptive methods such as Adam compared to something like SGD. And now, you know, something a little bit more subtle, which I'm not sure I'm going to have time to fully go into depth today, but some of you may be aware of this kind of idea that we really want to be looking not just at the performance on the training set, but we're interested in the performance on the test set much more than we are the training set. And there is kind of this intuition that we want flat, wide minima as opposed to sharp ones. And this actually gives better generalization. So the story is a little bit more complicated than this. I can go into this later. But one intuition, which is important, is let's say that I have my typical batch size B, and I start here at this point with the red arrow, and I go with a small learning rate to C. And this is very deep in terms of the training set loss, but it's very, very sharp, so it doesn't generalize so well. So instead, I come up with some heuristic learning rate procedure, which you can consider like simulated annealing in the physics literature, for those of you that are familiar, and I end up in minimum B or minimum A. Now, I want to basically cover that same type of trajectory if I have a larger batch size. So I need to use how basically the inverse of how my surface is transformed to get out of C star to B star. So this is why I think actually looking at the validation curves gives a much deeper insight as to whether we are traversing the loss surface in the same way compared to training. And, you know, this is just kind of shown here that you can, for example, if you're using SGD, you can scale with this square root scaling rule on the way up, which is now basically more conservative. And you might get this better training accuracy, but this significantly worse validation accuracy. So, of course, what you want is if you change your batch size, whether you go down or up, you actually want the testing result to be similar to that of the schedule you've already tried. Otherwise, it's not useful. So this is just worth saying that if I were to try this linear rule for Adam, not only does it completely diverge on the way up, we don't see anything super useful on the training curves because, of course, a neural network can always train with an arbitrarily small learning rate. But what we do see is we see that as we decrease the batch size and the learning rate according to this linear, not square root rule, what we see is a big difference here in the validation error trajectory. And we see consistently worse performance in validation error. I haven't shown the statistical significance because it would have made things messy, but these results are statistically significant. So any questions?
Sorry, but who is the best on the bottom plot?
This one here. So this here, you do get a slight improvement from 128 to 164, but this isn't super statistically significant. This is just one seed. But you see here, it gets consistently worse. From 32, 16, 8. I haven't plotted 4, but it'll be worse. Whereas you can see here, when I use the square root rule, that they all follow here very, very close results. And actually, the results get a little bit better as I go down lower and lower to 16 and 8. But that's simply because we're actually moving more aggressively in the surface, because at some point, when your batch size becomes small enough, your importance of the largest eigenvalue eigenvector pair will dominate this square root effect.
Okay.
Yeah, it's probably worth reading the paper, but you have this condition. You basically, your error in the flat direction must be basically worse than your error in the outlier direction. So this estimation here must be worse than this estimation there. But of course, as your batch size gets smaller and smaller and smaller, any small error in your estimation of the basically the largest eigenvalue eigenvector pair will begin to dominate, because this grows as the inverse of B, and this grows as the inverse of square root B.
Can we conclude that the best strategy is to use the largest possible learning rate, given that our neural network did not diverge?
Yes, this is not the focus of the paper, but that's typically the case. Yeah, so this is kind of what I was trying to talk about here, is that there was this idea that the largest learning rate that does train does give better accuracy and better testing. There was some initial work that argued it was to do with the distance from initialization. This doesn't actually hold when you have normalization measures. But the point that I'm trying to bring across is, let's say that you have figured out the largest learning rate that trains and gives great validation accuracy using your batch size of 1024 or whatever you're using. Now, instead, you want to train that same network on your mobile phone. And you already have your learning rate procedures. Is there any way you can scale that naturally without doing another grid search? And that's basically what my theory tries to argue. And this is why whether you use a kind of a linear or square root rule does actually matter. And what I'm arguing here is in the kind of typical changes that people look at. If you're using Adam, you should look at a square root rule. And if you look at SGD, you should be looking at a linear rule. Does that make sense?
Yeah.
May I have a comment?
Yeah, of course.
You've said about mobile phones, but actually it is not true that you will use something like ResNet on your mobile phone. It is more likely that you will have you will use some kind of sparse model. Is it fine to extrapolate your results to the sparse models? It seems that the Hessian for them will not be low rank.
Interesting things here. So I am actually trying to get a ResNet on the mobile phone. You can get ResNets on the mobile phone. So I'm not sure that first comment is true. Whether that's the most effective use of your resources, I don't know. That's another question. So then on your second question, have you looked at the Hessian? Can you show me that they are not low rank?
No, it's just an assumption.
So typically it's very interesting. So I have at different times when I've done this work been asked, okay, so on this network, will this matter? So nothing in my work assumes anything on the network structure. Now, I'm always happy to be shown wrong, but every time I've done the implementation, it's always stuck that way. So I would be very curious if you could show me a full rank Hessian of even a sparse network, I would be very impressed. Typically, even for your sparse network, my rank bound, which basically depends on the classes and the sum of the neurons, which is then for the rank will be divided by basically the product of adjacent layers number of neurons, will always be sparse. It might be a bit less sparse, but it's difficult for me to see how if logistic regression has 90% of its eigenvalues 0, the MLP 95, and then any ResNets on 99 plus, how any network that you're going to be actually using is going to be less sparse than logistic regression. This is not intuitive to me. So I would be very curious to see those results.
So thank you. That's quite a good comment.
I can send you the code, and I will eat my hat, and I will invite you for a drink in Moscow if I'm wrong, for sure. So I'm happy to see that. So anyway, back to proving your theories wrong. There is a small snag in the plot, and this is something that became clear to me actually at the beginning of the pandemic, because I spent so much time going through random matrix theory, and so much time basically plotting these spectral densities, that it became clear to me that we actually never see the spectrums of random matrices in neural networks, contrary to what's in the literature, including my own publications. So there are kind of two main assumptions that are done. One is, so you can split the Hessian into two matrices. One is just called this generalized Gauss-Newton, and the other one is this residual term. So just think of the Hessian as the generalized Gauss-Newton plus the residual. And now sometimes the Hessian is just modeled as a Wigner semicircle in total, and sometimes this residual is modeled as a Wigner semicircle. And so one thing I noticed is that even forgetting about this rank degeneracy and these outliers, both of which are nicely included into my theory. So this rank degeneracy, you can just think of the matrix as being embedded into a matrix of bigger dimension. This is not difficult. And the outliers are completely dealt with in the theory I've just presented. But what we see here is that in the log space, the Wigner semicircle is essentially flat, and then it cuts off. Whereas what we have here is we see actually in the log space a polynomial decay. Similarly so for this generalized Gauss-Newton. If this generalized Gauss-Newton is low rank, you have a very clear spectral gap between the origin and the first eigenvalue. And then again, it's a sharp cutoff and flat in the log space again until the cutoff. Whereas what we see here is a rank degeneracy and a polynomial decay in the log space. So this to me is fundamentally inconsistent. So I was at this time kind of confused because I had this theory that was somewhat nice. It seemed to experimentally explain the scalings of the learning rate and the batch size, which is what I was hoping to answer the whole time. I even had a new rule for Adam that worked well, was useful. And so I was kind of, what's going on here? And I was actually very lucky. A professor of mathematics in Oxford reached out to me, Sir John Keating, and he's actually head of the random matrix theory group, of which I've been made a key member. And he came to me and he basically said that in physics, we never actually see the Wigner semicircle law. What we see, what's known as universal, is essentially the k-point correlation function. So specifically the 2-point correlation function, which is essentially the spacings of adjacent eigenvalues. And so he was very curious as to whether we could see this in neural networks. So what we see here is that basically spacings between adjacent eigenvalues should follow this Wigner surmise instead of the Poisson for basically fully independent eigenvalues that don't have this repulsion. And we actually were able to show this. So you need the full eigen decomposition. So we're only able to do it for multi-layer perceptrons with a number of neurons up to 35,000. And we saw brilliant experimental agreement. And so this actually has been extended into another paper, which I'm on now, which is looking to be submitted anytime soon, that essentially the same results that I have here. Just go back. These same type of results can actually be derived not by assuming that the limiting spectral density of this perturbation matrix is Wigner, but simply that the local spacing law is Wigner's surmise. So, this is a collaborative work where I've mainly done the software engineering and experiments and provided some of the initial intuitions, but the maths is far more complicated than I would be able to do. And this has been handled by Oxford Maths, but it's nonetheless very pleasing that this inconsistency that I noted between the spectra and the results and the assumptions could be cleaned out. So now on to the next, any questions actually first before I move to the next topic? Okay, I think we're good.
Sounds very impressive.
Sorry?
Sounds very impressive.
Thank you, very, very kind, Dimitri. So something actually that I just wanted to present, given the interest at the time when I was in Moscow on stochastic weight averaging, is some work also done in conjunction with Oxford Mathematics on trying to understand SWA a little bit better. So for those of you that are familiar, I'm sure from the Bayes group with stochastic weight averaging, this is just going to be a very quick recap. But so iterative averaging, which had its history in optimization from Polyak and Nesterov, was often written off in deep learning, and it was considered didn't work. So it's just simply I run SGD, and at some point, either at the very beginning, in which it's known as iterative averaging, or near the end, it's known as tail averaging, I just basically take the average of my weights, and then I use that for my predictions. So in deep learning, it was initially considered not really to work. Instead, this exponential moving average, or the final point with a very extreme learning rate drop, was used instead. And it was instead kind of rediscovered as a new technique for generalization in what was called stochastic weight averaging, or averaged SGD. And what was kind of interesting for me is that there was limited theoretical justification for its ability to generalize, as opposed to what was already known in optimization. And it wasn't really combined with adaptive methods, sort of under the mantra that SGD generalizes best and we should just use SGD. So this for me was kind of a very interesting place to start digging to see if something interesting could come up. So the simplest way I started was just by considering a high dimensional quadratic model of the true risk and considering each gradient is just perturbed by like an IID normal noise term. And so under these assumptions, it's actually very easy to show that even if you decrease your learning rate or increase your batch size, you will, using that procedure, never converge to the true loss minimum, whereas you will if you use iterative averaging. And the interesting thing about this result is that it revealed a dependence on dimensionality. And this is something that we observed in practice. So in this curve here, we see basically the improvement of using something like SWA over its base optimizer, which would be whatever, SGD with some sharp learning rate drop, both of which are tuned. And we did really see this improvement that depended on the number of parameters in the network. And this was, again, this here is for CIFAR100, and this here is for ImageNet. And so this is very interesting that even this very, very simple model could reveal this importance of dimensionality. And those of you that work with deep learning are probably familiar that, we're often looking at bigger and bigger networks that do better and better. So this is particularly relevant. So the problem I had, of course, with my assumptions here is that they're obviously wrong. So if I move with a learning rate
idea.
of 0. Sorry?
Wait a minute. Could you please show again your theoretical result on SWA? So, do I understand right that it states that if you're not averaging, you will not converge to the minimum?
Yes.
But in stochastic weight averaging, we observe a bit different effect. So if we do not perform SWA, we are converging to the better train loss, but worse generalization. And if we conduct SWA, then our train loss becomes worse, but our generalization becomes better.
So this is sort of, I would say, the rabbit hole that I was careful to not go down, because it can get very ugly. Depends a little bit. So you're now looking at the difference between two surfaces. So very specifically here in my assumption, and the maths is going to get much more interesting. So this was just my first thought. I'm looking here at a high dimensional quadratic of the true risk. So I'm not interested at this point in your training loss. So I'm just looking at the quadratic of the true risk. And I'm saying that each gradient that I take is basically the gradient of this true risk plus some IID normal noise.
Okay, I understand. I just wanted to make a comment that this is not exactly what we observe for real train losses when we perform.
So I do actually have some curves on this. I can go find them. Is it not here? Okay, it's not in this talk here, but I have the curves on this. So what you have is, if you do a very, very sharp learning rate drop instead of using SWA, you'll get a better training result, but a worse testing result. That's what you're saying, right? And so I'm looking here at convergence to the true loss. Are we in agreement?
By true loss, you mean what?
Well, the true loss you don't have access to, but your validation loss or your test loss is an unbiased estimate of your true loss.
Yeah. Okay. So here's the theorem is formulated in terms of the true loss.
Yes.
Ah. Okay.
Now, of course, this is, it's very easy to get into discussion of how these two losses are related. Now, of course, for me, even though in the optimization literature, we look at the training loss, or is known as the empirical loss, is like an object of fundamental importance. I think philosophically, given that you have these very powerful function approximators that can completely learn random noise, I'm not sure that that's a very important object to be looking at. I think what we want to say is, and this is kind of what's called structural risk minimization, we want to always be thinking about minimizing our true loss, of which our test loss is an unbiased estimate. And anything we do is just in the context of the access to data we have. But the true loss is the object of real interest.
May I have a question?
Yeah, of course.
Is it true that you assume that your training gradient is different from the true gradient, the gradient with respect to the true loss?
Yes.
By the Gaussian noise?
Yeah, but this is about to be generalized. This was actually strongly improved by my collaborator in Oxford Maths. So this was just my first stab at the problem, but this is not particularly interesting because, as you've correctly identified, not only is the Gaussian assumption a little bit ridiculous, but the independence assumption is also ridiculous, because if I move with a learning rate of 0, then of course my previous gradient and current gradient are going to be completely dependent. And so by continuity of the loss, if I move with a very, very small learning rate, I'm going to basically have a very large dependence compared to if I move with a much larger learning rate. So my intuition here is that this essentially necessitates the need of these larger learning rates in SWA, which is what we were actually seeing in practice. But I couldn't get this from this theory. What I actually needed was to consider the covariance of the perturbations as a Gaussian process. And so if you consider essentially a stationary Gaussian process, as long as the number of parameters is much, much larger than the logarithm of your data set size, something that's met in practice, and your distance between the iterates is also to some extent kind of large, which necessitates the need of these large learning rates, we get very much the same result. So this is really already quite a pleasing result, but it gets better. Because, you know, one thing at the time that wasn't so well understood, at least for me, but, you know, probably my background in optimization was significantly weaker than that of some of the people here in the group. But, you know, a lot of people in SWA, there was also this confusion of, instead of averaging every iterate, they were doing what's known as a strided average. They're averaging once an epoch. And so what's clear from this kind of revised theory is that even though you have a little bit less variance reduction because you're averaging less frequently, because you're essentially moving at a greater distance in weight space, you also have less dependence between the iterates. And so these two effects counterbalance. And what's very interesting to see in practice, and we've run the experiments on this, if you use iterate averaging every iteration compared to once an epoch, this here is again on just CIFAR 100, but also we do it here for an LSTM on the Penn Tree Bank data set, you don't actually see any significant improvement. So actually, this is kind of a theoretical justification for averaging a little bit less frequently. And for those of you that are familiar with language models, there's actually a kind of heuristic training method known as checkpoint averaging, where you just save the checkpoints, and then for your validation, you just run through the checkpoints, specifically at the end of training. This is basically doing the same thing, and this kind of gives a nice little theoretical background for it. And so there was something else that wasn't really investigated at the time of SWA, but it does actually become a lot more important if you look at adaptive methods, adaptive gradient methods, was actually the importance of weight decay or regularization for iterate averaging. So there was a lot of comparisons made between iterate averaging and ensemble methods. So this is here showing the ensembles on the left. But quite interestingly, one kind of key difference is that ensemble methods, their improvement as the ensemble size increases is essentially the same, independent of the regularization used. So of course, the base learners are a little bit better if more regularization is used, but their improvement is essentially the same, whereas the same cannot be said for iterate averaging. So actually, interestingly, iterate averaging doesn't do that well if you don't have L2 regularization or weight decay. And it makes actually a very big difference, the weight decay that you use. So I don't have the plot here, it's in the original paper, but you will actually see that the improvement of something like stochastic weight averaging over just using a learning rate drop very close to vanishes if you don't use regularization. So it was interesting to see how we can bring this into the theory. So, you know, my initial hunch was perhaps that as I increase the weight decay, I maybe increase the distance between the epochs in weight space. But what we actually observed is the opposite. As I increase the weight decay and improve basically the performance of something like SWA, we actually decrease the distance in weight space. But what we increase is the relative distance in weight space. The distance in weight space divided by the weight norm increases consistently. So this can actually be brought into the theory just by considering a relative kernel under which the same result holds. And this is in the paper. And for those of you that are very interested in mathematics, I encourage you to go through it. It's a very nice proof. And this is the point where it actually gets a lot more interesting for me. So there was nothing in the theory that actually indicated that it was necessary to use SGD. In fact, as long as your adaptive optimizer is able to have some estimate, which is better than SGD, is what you assume, of the local Hessian, you'd actually expect the convergence in the true risk to be better. This is the theorem here, and I would again encourage you to go through the proof in the paper if that interests you. But the interesting result of this is that you can actually look at combining Adam with iterate averaging. You have to be a little bit careful with the weight decay that's used. So one reason it didn't originally work is because L2 regularization isn't as effective as just standard weight decay for adaptive methods, which is what we implemented. And what you can actually see here is that not only does Adam with iterative averaging and this kind of decoupled weight decay, you would say, beat the SGD baseline on well-known networks and data sets like ResNet 50 or ResNet 101 on ImageNet, but it can actually significantly beat SGD with iterative averaging, or SWA, as you want to call it. And what's actually interesting as well, and this is not shown here, is that this algorithm here, which we've called GADAM-X, actually requires reasonably less tuning to get good results. It works out of the box a lot better. This is something that's kind of been remarked in terms of adaptive methods. They typically work with less tuning, but with more tuning, usually SGD does better. Whereas here we can see that actually our method tune does even better. And so here are the results. And it's really worth mentioning the magnitude of these results. So, a lot of people get their knickers in a twist as to whether they should be using a step schedule or a linear schedule or a cosine schedule, which is very popular today. The cosine schedule over the step schedule adds in the order of 0.2% on the top one test accuracy. Whereas we have nearly a 2% increase using just optimization alone. We haven't modified the network. We haven't modified the loss function. We haven't modified the augmentation procedure. We haven't used advanced pre-training methods. And so it's really hard to understate that the power of these results using simply the combination of a few tricks, which we've devised a little bit of a theory for. I also have a hunch this will work well for NLP tasks. This here is just shown on a simple LSTM on PTB. I also implemented GADAM for Huawei team on NLP and found some pretty reasonable results that should also be coming out soon. And so any questions?
Could you please once again summarize the idea of GADAM-X?
It's just use Adam with iterative averaging and decoupled weight decay. Simple as that.
And what does it mean, decoupled weight decay?
Yeah, I probably should have put this in the slide. So if you think of L2 regularization, you add a kind of term gamma weight norms squared to your loss. Yeah.
Right.
So when you differentiate that, you end up basically having like 1 minus gamma times your weight, and then you have some gradient of your loss.
Yeah.
Yeah. Whereas if you have an adaptive method, your gradient update is no longer minus alpha gradient, but it's minus alpha inverse of preconditioning matrix gradient.
Yep.
So you wouldn't have 1 minus gamma times your weights. You would have 1 minus gamma b to the minus 1 your weights. Yeah. If you just did. So there was this paper, and I have actually written another paper on this, but I just didn't think it would be as interesting. So it's a big question. Is like, why, if I just use this kind of classical weight decay instead of L2 regularization, does it help Adam do so much better? That's basically the point. This multiplying by the inverse preconditioning matrix makes your regularization much worse.
So you're not using preconditioner in L2 regularization term, right?
Yeah. So it's interesting. It's actually not really clear why that does better. You could argue maybe from a maximum entropy perspective that if you use this inverse preconditioner matrix, you're basically making some strong assumptions as to, it's like having a strong prior as to which parts of the weight you should decrease and which not. Whereas like a maximum entropy prior would just decrease all weights similarly.
Interesting. And do you have already a paper on GADAM-X?
Yeah, I do. This is actually also under review at JML Lab, but I'm happy to send that. That's actually quite well written. So I'm happy to send that.
Please do.
Yeah, happy to get comments. So any more questions?
Sorry, but can you clarify the difference between GADAM and GADAM-X?
Yeah. So GADAM is basically just what I've explained. And then GADAM-X, this is a trick that I probably wouldn't even find as interesting now. But have you heard of the optimizer PADAM?
No.
Okay, so
No.
you know, in Adam, you basically have SGD with momentum, but you also basically scale each component by this inverse of the square root of like the exponential moving average of the gradient squared.
Uh-huh.
Yeah. So there was this paper that had some pretty nice results, but didn't make it into ICLR, that was called PADAM. And it basically said, well, if I, instead of using the square root, I use a slightly smaller power, maybe I can get something in between Adam and SGD.
Uh-huh.
So instead of using a square root, you could use a quarter or an eighth.
So
Yeah?
you're using just a smaller power.
Yeah. So it's actually, so this was at the time, at the time when I was writing this paper, I was interested in showing that adaptive methods were not necessarily worse than SGD, right? And it was very interesting, this theory, and then combining that with iterative averaging. And for me, just being able to do better than SGD, or being able to do better than SGD with iterative averaging, was already great. And the fact that it needed less tuning was also great. I was also a little bit confused why we were using this slightly different power to a half. But the argument basically goes as follows. So in kind of stochastic second order methods, or you could even say full second order methods, your power is basically 1. You have basically just the full inverse of the matrix. Whereas in something like Adam, it's square root. This comes from the regret bound in Dushi. And it's like the 2011 paper, they derived that regret bound, and that's where the half comes from. But you could also think of this power of a half as basically being more conservative about your curvature estimate, right? So you could be more you could be more conservative still, right? And there are 2 ways of doing that. One is to basically reduce that power, and the other one is to increase your numerical stability or damping constant. Both give essentially the same result. Does that make some sense?
Quite a bit.
Yeah. So I would say in the future, I wouldn't even bother with, if I had known what I know now, I wouldn't have bothered with this GADAM X. I would have just stuck with GADAM, but I maybe would have tuned my numerical stability constant a little bit more. Because a numerical stability constant that's greater than 10 to the minus 8 can often actually give significantly improved results. And it doesn't really hard convergence either. So that's actually a mistake in practice, that people keep it at 10 to the minus 8. And you see a lot of papers that are very results focused will use a slightly different value. Maybe they'll use 10 to the minus 4, or 10 to the minus 5, or 10 to the minus 3. And I'm actually just submitting a paper at the beginning of next week. It's going to be a random matrix theory and physics journal that looks at a random matrix theory approach to this damping or numerical stability constants. I'm happy to share that with you if you'd like. So I think we're nearly at the end. I wanted to basically just share with you a little project that I was actually developing that might be of interest for people that wanted to collaborate in maybe a non-academic setting, if that's of interest. I don't actually know if it's going to work as well as I'd hoped, simply because I'd raised some money for this in Switzerland, and so I would have been able to fund interns or contractors. I don't know with the situation in Russia now whether that will be possible at all. I still have some money tied up in Russia, but I don't know how that's going to work. But I just wanted to share something quickly that's kind of been a big passion of mine also for a few years, even when I was under Dimitri's guide in Bay's group back in Moscow. I was actually training for a competition to basically be a top-level sportsman in Oxford, and I was powerlifting. So you can see me here doing 205 kilos. And something that was of interest to me back then and has become a larger project since is to what extent can I do automated coaching or training using deep learning computer vision. And so what I have here are just some 2 basic components. One is basically using body detection. This, you guys might be familiar with key point estimation or dense pose by Facebook. So I basically just put in a video and find the body and then make analysis based on the movement of the body. And I also look at the movement of the barbell here. And here you can see it's like a velocity tracker. But maybe I can show you guys a video. It'll maybe a little bit more clear. Be something like this, you know, you'll see me doing that. And what you see, which is quite nice, is so basically from the velocity profile, you can actually understand how difficult the lift is for the person. So for a lighter weight, this is 205, the maximum I've done is 210. For 180 or 190, you will see a nice U shape. And as it gets more difficult, you have this sticking point here. And so I was basically just intrigued to what extent it's possible to automate this entire training process and have that running on the phone. And that's the project I'm doing now, if you're interested. And I'm just going to show you a little thing that I've built, which I think is actually very useful for people that train to not hurt themselves. So one often cause for pain in lifting is just incorrect technique, specifically for something like the deadlift. You have a kind of curvature of the spine. And here you can see this is me with a very offending example compared to a straighter example. And I was just kind of curious whether it was possible to create a kind of a nice engineering solution that could do this in general under different lighting conditions. And something here, which is actually super easy, is just by assuming that the kind of edges here at the back were basically the chord of a circle. And this here was essentially a sector. I could calculate out the radius of the circle in pixel space. And by, of course, the radius is not invariant to your position near the cameras. Of course, if you're further away, you'll have a smaller radius than if you're closer. So I needed to divide it by something else that was kind of fixed in the frame. So one thing I considered was just the size of the barbell, but of course, this would now give a bias towards larger lifters compared to smaller lifters. So I just considered the dimensions of the head. And this gave actually pretty nice, consistent results at saying basically like how straight you were. So basically this metric essentially tells you how curved your back is. So that was just a project that I'm, still keen to work with on people if you're interested. I don't know how the funding will work because of the situation right now, but that was something I wanted to present. So if you guys have any questions about anything, do just ask now. I don't know if we are out of time, or do we still have a moment to ask questions?
We'll have several more minutes for questions,
Okay.
if any.
I have a small question actually about your GADAM again.
Sure.
You've said that you are using weight averaging. Do you use it with like high frequency or with low frequency?
Was just once an epoch. As shown in these experiments here, it doesn't really make a difference.
Okay.
What matters a lot more is when you average and what learning rate schedule you use with your averaging. One thing that was interesting, so it's worth saying, so the first time I ran GADAM-X, I beat the SGD typical result, and that's like unheard of usually for an optimizer. So then of course with tuning, it got better. One thing that made a really big difference was starting with a very, very large learning rate and then dropping it down to a smaller amount. So that basically a more aggressive simulated annealing worked very well. Now, why that worked so well for GADAM or GADAM-X and didn't work for SGD or SWA is kind of an open question. My hunch is that you can just move more effectively with big steps in the loss surface without diverging using adaptive methods that you can with SGD.
Mm-hmm. So, okay, thank you for your gorgeous talk.
Okay, well, thank you.
Yeah, I would also like to thank Diego. For those of you who got interested in his startup project, please don't hesitate to contact him, and I may provide the necessary links.
Yeah, maybe. I don't know if I have my email on.
Yeah.
Yeah, I think maybe you can just forward my email if they're interested.
Okay, I'll do. As for me, I'm a bit overwhelmed with the amount of material. And just one critical remark, Diego, it seems to me that, you show so many theorems, and you show it very, very quickly. So it's quite problematic to understand them during the short period when you are showing us the corresponding slide. So I would advise you to provide some informal description of the main theoretical results, because it will simplify the understanding during your talk. I realize that these are important theorems, but it's much better to understand them when you read a paper, not when you listen a short presentation. So I think that it will improve your talk, and will make it much more understandable. Because currently I'm a bit overwhelmed with the material, but I'm very interested. So please send me at least the paper with the GetMX, because I was also wondering how to explain the success of stochastic weight averaging, and it seems that you've made impressive progress in explaining it. So I would happily have a look on your results in a more quiet way when I have a opportunity to just to read the paper, to slowly read the paper and trying to understand all of your theoretical tricks. Okay.
Yeah, thank you for your feedback. Yeah, I agree. I wasn't sure, what would be interesting for the group. So I thought I would present more, not less material. So I'm sorry if I got that wrong. I originally was going to do just, random matrix theory and maybe just 2 minutes on this startup project, but I just remembered how we spoke about stochastic weight averaging back in the day. So I just kind of fitted that in for you, and maybe it ended up being a little bit rushed. So yeah, I do apologize for that. So do let me, I will send you the paper right now at the end of the talk, and I'm happy to take any questions.
Okay, thanks a lot.
Okay, send me the
you.
talk recording, by the way.
Thanks for Green and making presentation for us in these difficult times. It's important for us to feel that we're not in complete isolation, and that foreign colleagues are still willing to cooperate with our research seminar. So that's important. Thanks, Diego.
Yeah.
And as for other guys, I just wanted to make an announcement about our next talk in a week. The speaker will be Chingir from our group, who will give a talk about denoise diffusion restoration model, which is a follow-up on state-of-the-art diffusion models that is able to perform various conditional generation problems. So it should be also quite interesting. So thanks for everybody. See you in a week. Bye.